All right, so let's take a look at section 6.3, which is on the inverse trig functions, our last lesson for this unit. And since we have six trig functions, of course, we know about cosine, sine, tangent, and then the three reciprocal functions, cosecant, secant, and cotangent. And each of them has its own inverse function. So remember we talked a little bit about inverse functions earlier in the semester, and I want to refresh your memory on what we meant by an inverse function, what were some of the characteristics of functions that are inverses. And one sorry, my dog is in the background, so you might hear him. One thing that was really important in order for a function to have an inverse in the first place was that it had to be what we called one-to-one. And the way we tested to see if a function was one-to-one is we used what was called the horizontal line test. So remember, the horizontal line test says that as long as we have a function that if we were to draw a horizontal line through the function, if it hits the graph at more than one location, then it fails this horizontal line test. So this is just the basic sine function, a graph of the basic sine function. You can see as is, because of the repetitive nature of the function and the peaks and the valleys in the graph, this would fail the horizontal line test the way the graph is. So for that reason, what mathematicians came up with is they said, okay, what we're going to do is, instead of looking at the entire sine function all the way out on the domain of all real numbers, we're going to restrict it and only look at one piece of the function so that it passes the horizontal line test. And here's what they did. So this would have been the portion of the sine curve that they would have looked at. So if we restrict the sine curve, so instead of taking this whole thing, what they're really looking at is they're looking at it from right about here to right about here, and that little window right in there is all they're going to look at. Okay, and so here's a zoomed in version of that. That's that same window, and this actually goes from negative pi over 2 to positive pi over 2. So if we restrict this to look at it from negative pi over 2 to positive pi over 2, you can see that now this does pass the horizontal line test, right? And so what we've done is we've restricted all 6 of the trig functions and only looked at them over a small window so that they would pass the horizontal line test. And that's how we define the inverse functions for these 6 trig functions. So here's a graph of the inverse sine function. Let's talk about notation for a minute. So if the original function is the sine function, the inverse, remember the notation for the inverse looks like this, the general notation for an inverse function. For inverse sine, we would write it this way. Another way we'd write it, there's actually 2 notations that we're going to use interchangeably, is we'd use what's called arcsine. So this is also called the arcsine function. When I talk about it in class, I usually just say arcsine, but sometimes I'll write arcsine notation, or I'll write this little sign with a little -1 notation. And remember that with inverse functions, the domain and ranges are all reversed. So if the original sine function we looked at the restrictions, the original sine function would have had a domain that ranged, or I shouldn't use that word, the domain that went from negative pi over 2 to pi over 2. This is the original sine function. The range, the low to high value, so the lowest y value to the highest y value. Remember, with the sine function, it's -1 to 1, right? Okay, so with inverse functions, the domain and range are all swapped. Remember that from earlier in the semester. Domain and range are literally reversed. So if that's the domain and range for the sine function, then the domain and range for the inverse sine function. So here's the graph of this. I've called it arcsine here, so I'm going to use that notation. So here's the graph of arcsine, and notice that the domain and range are swapped. So the domain this time is going to be from -1 to 1, and the range is going to be from negative pi over 2 to positive pi over 2. Okay, and so when we look at the graph of it, this lowest y value here, literally the graph just stops. This would be at negative pi over 2. The highest y value up here would be at positive pi over 2. And then that's your range. Your domain, you can see it goes from -1 to +1 because literally everything is reversed, okay? So all of the 6 trig functions, the inverse trig functions, are going to be defined in a similar way. We're going to restrict the original functions so that they pass the horizontal line test, and then we're going to swap the domain and range literally. What does it mean when we see this notation? So when we're asked to evaluate something like this, if I said, what is the arc sine of -1/2? Remember, everything is in reverse. Everything's opposite. So if I said, what is the arc sine of -1/2? This would be equivalent to asking yourself, what angle on the unit circle within our restricted range has a value of -1/2? So in other words, where does sine on the unit circle equal -1/2? And if you think about the unit circle, sine would equal negative. First of all, sine would be negative in which quadrants? Sine, if I'm talking about. Sine would be negative in quadrants 2 and quadrant 3. And sine would be negative at, or sine would be 1/2 at your, let's see, at your pi/6 locations, right? And so, I'm sorry, wait a minute. Hold on, scratch that. I've got the quadrants wrong. This was cosine, not sine. Scratch that. Let me get rid of that. Where is sine negative? Quadrant 3. As soon as I said that, I was like, got the range wrong. So let's check that. Sine would be negative in quadrant 3 and quadrant 4. My bad. I was thinking of cosine. Sine would be negative in quadrants 3 and 4. Okay, so sine would equal 1/2 at those pi/6 locations. So sine would equal -1/2, for example, at 7 pi/6, and then again at 11 pi/6. But here's the trick. Remember, my range is only from -pi/2 to pi/2. So pi/2, of course, is up here. Negative pi/2, it's a negative angle, would be negative down, pi/2 would be down here. So when you're looking at the sine function, the inverse sine function rather, your answer needs to be in either quadrant 1 or quadrant 4. But I want the one that's negative, so I have to go with the one that's in quadrant 4. Here's the hitch, though. You're not going to tell me 11 pi/6, because 11 pi/6 would be all the way around in the fourth quadrant. I want to go backwards. I want the same angle at the same location, but I want it to be within the range of -pi/2 to pi/2, so I need to go backwards. So the value where sine equals, or the angle where sine equals -1/2, within this range would be at pi/6. So arc sine of -1/2 would be at pi/6. Let's just kind of recap what we said. It's equivalent to saying, where does sine equal -1/2 at what angle, but it has to be within this range. So I had to go backwards to get the negative angle that's in the fourth quadrant. If you tell me 11 pi/6, I'm going to mark that wrong because that's not in the range. It's got to be in this range in order to fit the definition, okay? Because remember, it's got to be restricted from -pi/2 to pi/2 for your output values. Let's try another one. Arc sine of √3/2. So this would be equivalent to asking yourself, where does the sine function equal √3/2? So start by thinking about which quadrant it would have to be in. It's got to be in the first quadrant or the fourth quadrant if I'm talking about arc sine, because it's got to fit in this range, right? It's positive, so therefore it has to be in the first quadrant. So where in the first quadrant does sine equal √3/2? And of course, that would be at your pi/3 values. So the unit circle values are really important. Those are going to come back over and over again. This is why I said, learning where those angles are is so important. And then letter C here says, where does inverse sine? So basically, inverse sine or arc sine of 2 is the question. That's like saying, where does sine equal 2? Well, remember, our sine function, the range of sine is only from -1 to 1. So does sine by itself ever equal 2? And the answer is no, it never does. So this one we can say is, I don't know, what can we say? Doesn't exist, or not defined, or D&E does not exist, something like that. So this is an impossible question. There is no arc sine of 2 value. It just doesn't work. Okay, so let's talk about the other trig functions and the restrictions that go with each of these inverse functions. So we started with sine. Let's just talk about that. So I'm going to use the different notations. So we have arc sine, inverse sine of x, or we may call it arc sine. I'll write both on here. Either notation is fine, and most textbooks go back and forth between the two notations. So the domain we said was -1 to 1, and the range we said was from -pi/2 to pi/2. Okay, so the thing to remember that I find helpful anyway when I'm doing these is to think about the quadrants. That means you're in quadrant 1 or quadrant 4 when you're talking about inverse sine values. Cosine, so inverse cosine looks like this notation, and the domain would be the same, -1 to 1, but the range is a little different. So for inverse cosine, it's going to range from 0 to pi. Okay, so from 0 to pi, and you can think about inverse cosine is in either quadrant 1 or quadrant 2. And then tangent, so let's do inverse tangent, or arctan is the notation. So let's think about that. So the domain for inverse tangent is going to be from -1 to 1 again. Let me think about that picture. It's going to be from -1 to 1 again. Actually, hold on. Wait a minute. Let me check this one real quick. So let me go back to what we know about tangent for just a second. Tangent graph, remember, looks like this. Oops. So the tangent graph, the original tangent graph, looks like this, right? It goes up on the right, down on the left, from -pi/2 to +pi/2. So if we reverse those, okay, now I got it straight. So the domain, so the original, this is the tangent graph, right? This is the original tangent graph. The original function has a range. Let's start with that because remember, domain and range are all swapped. The original function has a range that goes, it's all real numbers, right? So from -infinity to infinity. So that becomes the domain for the inverse function. So -infinity to infinity. And then the range would be the domain of the original function. So that'd go from -pi/2 to pi/2. But so it's the same as it is for sine. The only difference is it does not include the endpoints. And the reason is because the tangent function, the original tangent function, had asymptotes at -pi/2 and pi/2. But it's the same quadrants as the original arcsine function, which will help you kind of keep those straight. Okay, so then we've got the other three, which are less common. We're not going to use these quite as often. I'm not going to make you memorize these or anything like that. I'll probably give you this chart on the test so you don't have to worry about remembering them. But I do just kind of want you to get comfortable with them as we practice. Let's do the other three. So the inverse, let's see, so arc, which one do we want to do first? Doesn't matter. The inverse reciprocal of sine would be cosecant. So let's do that one next. Let's do inverse cosecant function. I guess it would look like arc cosecant. And then let's think about the graph for cosecant for just a moment. So cosecant is the reciprocal of sine. So if the original sine curve looks like this, right, and we would restrict it from here to here, then the cosecant curve would go from here to here, right? So the cosecant curve would just be this branch and this branch. And we would restrict it. It would have the same range as, or the same, the output would be the same as it was for inverse sine. So it would be from -pi/2 to pi/2, but it would not include the endpoints because at pi/2 and pi/2, let's check. Yeah, so it would go from -pi/2 to pi/2. So it'd be the same range as its reciprocal function. Now, the domain, though, is the opposite. So instead of being from -1 to 1, the domain, because we want these values down here and these values up here. So the domain would be from -infinity to -1. And then again, on the other side, from +1 to infinity. And we'll talk about this a little bit more in class. I don't think this is going to be a problem for you. Let me keep going. Let's do the last couple. So secant, so the inverse secant function. So secant, remember, is the reciprocal of cosine. So arc secant. The domain, the range is going to be the same as it is for cosine. So from 0 to pi. And then the domain is going to be the same as it is for arc cosecant. So it's going to be from -infinity to -1, and then from 1 to infinity. Okay. And then last but not least is cotangent. So inverse cotangent or arc cotangent. All right. So it's going to have the same domain as the tangent function, -infinity to infinity. The difference, though, is going to be how the tangent function is defined. Let me draw you a quick sketch here. and just remind you of what the tangent function looks like. Just one cycle of the tangent function. Okay, so the tangent function, fix that. So the tangent function, remember, goes up on the left, down on the right, but it's got asymptotes at 0 and at pi. Remember, at 0 and at pi. So that's going to be your range for your arc cotangent, is from 0 to pi, but it's not going to include the endpoints because of those asymptotes. So it's going to look like that. Okay. And like I said, I'll provide you this chart on the test. However, I do expect you to at least remember the ranges for the first 3. If you remember those, that's going to make things a little bit easier for you as you're going through the problems. So let's do some examples of what we're going to be asked to do with this. Evaluate arctangent of -1. So this is like saying, where does tangent, this is kind of the way you'll think about, where does tangent equal -1? But the trick is it has to be in quadrants 1 or 4. Remember, it's got to be in this range. That's so important. It's got to be from -pi/2 to pi/2. Okay. So, and if it helps make a little sketch, that's fine. So it's negative. That means it has to be in quadrant 4, right? Tangent wouldn't be negative in the first quadrant, so it must be the fourth quadrant. So we want to go backwards into the fourth quadrant. And I want the location where tangent would equal 1, but in the fourth quadrant going backwards, so it's going to be negative, and it would be the pi/4 angle. So it would just be negative pi/4, right? So that would be the angle in quadrant 4 in this interval that would have a tangent value of -1. Arc cosine. So again, this is like saying, where does cosine equal 0? Arc cosine of 0. So, okay, so between 0 and pi, so in other words, think about it on your unit circle. I'm going from 0 to pi. So in quadrants 1 to quadrant 2, right? Because that's the range for arc cosine is 0 to pi. Where does cosine equal 0? So that would occur up here at the pi/2 angle. So the value here would be pi/2. Number 4, it says to solve this equation. So it's an arctangent. And remember, inverse functions undo each other. So what you can do here is you can just say, all right, let's do some algebra on this, and let's literally take the tangent of both sides. So if I take the tangent of arctan of this expression, and I set that equal to tangent of pi/4. So literally, I'm taking the tangent of both sides. These will undo each other and just leave you with 2x minus 3. So 2x minus 3 equals tangent of pi/4. What is the value of tangent pi/4? The first quadrant, pi/4, that's where tangent would equal 1. And then just solve it, of course, like a normal equation, and I get a value of 2. So this little property, though, of taking the tangent will work, because, as long as you do it to both sides, of course, that works because you're undoing the inverse trig function. Okay, number 5, let's evaluate each of these. Arc sine of √3/2. I think we actually did this one earlier. Arc sine of √3/2, the same one, but that would be in the first quadrant because sine is positive. Basically, if these are positive, you're in the first quadrant. It has to be based on the ranges. And that would be where sine equals √3/2, which would be at the pi/3 value. Arc cosine of negative √2/2. So again, think about which quadrant that would be in. If cosine is negative, remember what your range is for cosine. It has to be in quadrants 1 or 2. Well, if cosine's negative, it has to be quadrant 2. So that means in quadrant 2, where does cosine equal √2/2? So that would be the pi/4 value in the second quadrant, which would be 3 pi/4. And I want you to note that 3 pi/4 is indeed in the interval 0 to pi. It has to be. Your output here has to be in that interval. Okay. Arc sine of 3, remember we said that that would be like saying, where does sine equal 3? But because the range of the sine function is only from -1 to 1, this is impossible. Can't be done. No such thing. Doesn't work. So we'll skip that one. The next one, arc secant of √2. So the first thing I would do is probably, I wouldn't even deal with the secant. I would probably change this to its reciprocal function. So its reciprocal function, its secant, of course, is the reciprocal of cosine, right? So another way of asking this is, where does inverse cosine or arc cosine of the reciprocal of √2? So the reciprocal, this is √2/1. Reciprocal would be 1/√2. And more familiar to us would be √2/2, right? So this is equivalent to saying inverse cosine of the reciprocal of √2, which would be √2/2. over 2. Make sure you see what I'm doing. This is the reciprocal of the original value they're asking, and I'm using that because I'm really going to do the reciprocal function. I don't want to deal with secant and cosecant. I'd rather deal with cosine and sine, right? Those are the ones we're familiar with, so those are always the ones you want to fall back on. So really the question is, okay, where does cosine equal root 2 over 2? Well, it's positive, so it has to be in the first quadrant, which means I'm looking at the pi over 4 value. Okay, so when you have these inverse let me watch my words very carefully because inverse and reciprocal are very different. When you have these reciprocal functions, go back to the originals and change the reciprocal of what's in the argument. So cosecant, for example, that's the reciprocal of sine, right? So what I'm really going to ask is where is the inverse sine value at what location? So I'm going to find the reciprocal of this expression. It's negative. I'll leave the negative in there. Root 3 over 3. So if I flip that, that would be 3 over 2 radical 3. And I'm going to clean that up so it looks more like something we're familiar with on the unit circle. I'm going to rationalize the denominator. So that gives me 3 radical 3 over 2 times 3 would be 6. And then, of course, that reduces to root 3 over 2. So in other words, the reciprocal of this expression is root 3 over 2. And so that means I'm really looking for the inverse sine value of root 3 over 2. Okay, so all right, let's think about what quadrant it has to be in. It's negative, so inverse sine negative has to be down here in the fourth quadrant. So working backwards into the fourth quadrant, that would be negative. Where does sine equal radical 3 over 2? Has to be the pi over 3 angle, so it's going to be negative pi over 3. It's going to be our value. Okay, let's see. Evaluate each of these if possible. So let's try the first one. It says tangent of arc tan of negative 5. Well, this is kind of like we talked about earlier. These will undo each other, right? Tangent of arc tan is going to undo each other and just leave us with negative 5. The rest of these, let's be a little bit careful here about what's going on. If I just try to apply the same logic to this one, arc sine of 5 pi over 3, and just say the answer is 5 pi over 3, I have a problem because 5 pi over 3 is not in the range for arc sine. So when you recognize, see how negative 5 is just kind of a generic number, but the rest of these, you see, these are values that show up in our unit circle, 5 pi over 3 and pi. If you see that it's a unit circle value, I think a better strategy for this is to kind of work your way from the inside out. So start on the inside and evaluate sine of 5 pi over 3. So sine of 5 pi over 3, so this whole thing is going to be equivalent to arc sine of whatever sine of 5 pi over 3 is. So think about your unit circle. 5 pi over 3 would be in the fourth quadrant, right? So in the fourth quadrant, the sine value at pi over 3, we know it would be negative because you're in the fourth quadrant, and it would be root 3 over 2. So this becomes negative root 3 over 2. So make sure you're clear on what I did. I calculated the value for sine of 5 pi over 3 from the unit circle, and I noticed that that was negative root 3 over 2. So now the question becomes, what is the arc sine of negative root 3 over 2? And here's where we're back to our ranges. If I'm looking at arc sine and I'm negative, that means I have to be in the fourth quadrant. But I have to go backwards. So this would be negative pi over 3. And so you see why I can't just say, oh, these undo each other, it's 5 pi over 3. The problem with that would have been that 5 pi over 3 was not in the range of arc sine. So you kind of have to work through it piece by piece to make sure you get the number that's in the correct range. Let's do another one. Cosine of arc cosine of pi. All right, so this is a little strange. Let's think about working our way from the inside out. If I want to evaluate arc cosine of pi, that would be equivalent to saying, where does cosine equal pi, right? We'll pause and think about that for a second. Cosine, not cosine of pi. Notice the difference between this question and this question, right? This is asking, where does cosine equal pi? But remember, the range for cosine is negative 1 to 1. So does cosine ever equal pi? No, not possible. Can't be done. There is no such thing. So we're going to say NA can't do this problem. So you see this is not defined, therefore I can't evaluate the rest of the question. Okay? Now, look at the difference here. Can I evaluate cosine of pi? So what is cosine of pi? That, of course, would be negative 1. So then this question becomes, arc cosine of the value for cosine of pi, which is -1. So on the unit circle, think about where does cosine equal -1? Remember, it's got to be in our range. Cosine, the range is from 0 to pi. Well, it only happens at one location, and that would actually be at pi. So notice in this example, pi was the answer, but I think for these, you're better off starting on the inside and working your way out, just in case something is undefined and to make sure that you get everything that's in the correct range. All right, these next couple of questions, we're looking at values that are not unit circle values. So it says evaluate by sketching a triangle in the appropriate quadrant. So start on the inside again, just like we did in the previous questions, arc cosine of 2/3. So this is the angle, right? So if I want to evaluate arc cosine of 2/3, that's like saying I want the angle whose cosine value is 2/3. It's a positive cosine value, so arc cosine is positive. That would have to be in quadrant 1. So I'm going to draw a little picture here. I'm going to draw a triangle in quadrant 1. Remember back at the beginning of chapter 5, we drew these triangles and we said you always make the angle with the nearest x-axis. That's called your reference angle, and that's the angle we use for theta. If cosine is 2/3, remember SOHCAHTOA, that means the adjacent side is 2 and the hypotenuse has to be 3. So we're going to figure out the opposite side using Pythagorean theorem. So 2 squared plus, we'll call this y squared equals 3 squared. So 4 plus y squared, of course, equals 9. Y squared equals 5, which means this has to be the square root of 5. So now that you have your triangle labeled, what I want you to remember is this is an angle, right? This represents an angle whose cosine value is equal to 2/3. So then the question becomes, what is the tangent of this angle? So using the same angle, go back and look at your triangle. And remember that tangent is opposite over adjacent. So this is going to be √5/2, right? Opposite over adjacent. So once you've got your triangle set up and labeled, you're good to go on these. The trick is getting your triangle labeled in the correct quadrant. Let's do the last one. So let's think about where we need to draw this. This is the angle theta, whose sine value is equal to -3/5. So where is this going to be if I'm talking about arc sine and I want arc sine of a negative value? This has to be in the 4th quadrant. So we're going to put it in the 4th quadrant. And so my reference angle has to be made with the nearest x-axis. So I'm going to drop my perpendicular here and put my reference angle right here. Now, get this labeled. The sine of this angle is -3/5. So SOHCAHTOA, again, sine would be the opposite. And that's got to be negative because it's going down. And then the hypotenuse is always positive, so that has to be 5. The adjacent side is what we're looking for. So the adjacent side, this is actually a Pythagorean triple. If you recognize it, this would be a 3, 4, 5 triangle. If you don't recognize it, just write it out and use Pythagorean theorem. They're looking for the secant of this angle. Secant is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, secant would be hypotenuse over adjacent. So then the result would be 5/4. But getting the triangle is the trick on this. All right. And I know there's a lot of information in this section, so we'll do plenty of practice in class and we'll see the different kinds of problems we're going to do. The biggest thing I would focus on right now is remembering for these first 3 functions, remembering what these ranges are, because that's going to make things a lot easier for you as we go through these examples.